Imagine holding a sugar cube in your hand. It's small, light, and seems insignificant. Now imagine that this tiny cube weighs more than every single human on Earth combined. That's the mind-blowing density of a neutron star. These stars are so dense that it is almost incomprehensible. A sugar cube-sized piece of neutron star matter would tip the scales at a staggering 1 trillion kilograms, a testament to the extreme physics at play in these celestial objects. It's like trying to imagine the weight of a mountain in the palm of your hand. Neutron stars are among the most extreme and fascinating objects in the universe. They are the remnants of massive stars that have reached the end of their lives in spectacular supernova explosions. These explosions scatter elements across the cosmos, seeding new stars and planets. These stellar corpses are incredibly dense and compact, cramming more mass than our sun into a sphere just a few miles across. They challenge our understanding of physics and the universe. Stars are cosmic furnaces, powered by nuclear fusion in their cores. This process fuses lighter elements into heavier ones, releasing enormous amounts of energy. Our sun, a relatively average star, fuses hydrogen into helium. For stars much more massive than our sun, their evolutionary path leads to a more dramatic fate. As these massive stars exhaust their nuclear fuel, the outward pressure from fusion can no longer counteract the inward pull of gravity, and the star's core collapses violently, triggering a supernova explosion that can outshine entire galaxies. The core, crushed under immense pressure, forms a neutron star if it's massive enough. While the thought of our sun exploding might be alarming, we can rest assured that our star won't become a neutron star. Our sun simply lacks the mass for such a dramatic end. As our sun ages, it will eventually expand into a red giant, engulfing the inner planets, including Earth. Eventually, our sun will shed its outer layers, leaving behind a dense Earth-sized core called a white dwarf. This stellar ember will slowly cool over billions of years, eventually fading into a black dwarf. So, while our sun won't experience the explosive fate of a neutron star, its evolution will still have profound effects on our solar system. Neutron stars are incredibly small, with diameters typically around 12 to 20 kilometers, about the size of a city. However, don't let their size fool you. These objects pack an unbelievable gravitational punch. The gravity on a neutron star is billions of times stronger than Earth's gravity. The atoms within a neutron star are crushed together due to the density, with protons and electrons combining to form neutrons, hence their name. Not all neutron stars are created equal. They come in various forms. Some exhibit fascinating properties that set them apart from the rest, making them unique cosmic phenomena. Pulsars, for instance, are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. These beams are incredibly precise. Like cosmic lighthouses, they sweep across space as the neutron star spins, creating a rhythmic pattern. If Earth happens to be in the path of these beams, we detect them as pulses of radiation, which is how they got their name. This regular pulsing can be used to study the cosmos. Magnetars, as their name suggests, are neutron stars with incredibly powerful magnetic fields. These fields can distort their surroundings. They are trillions of times stronger than Earth's magnetic field, creating intense magnetic storms. Magnetars can unleash bursts of high-energy radiation, making them some of the most energetic objects in the universe. When two neutron stars in a binary system eventually spiral towards each other, they collide in a catastrophic event called a kilonova. This collision releases an immense amount of energy, creating a spectacular display of light and radiation. These explosions are some of the most powerful in the cosmos, briefly outshining entire galaxies. The sheer brightness of a kilonova can be seen across vast distances, making it a significant event for astronomers to observe. Kilonovae are thought to be the cosmic forges where heavy elements, such as gold and platinum, are created. These elements are scattered across the universe, contributing to the formation of planets and even life itself. The 2017 detection of gravitational waves and light from a neutron star collision, dubbed GW170817, provided compelling evidence for the existence of kilonovae and their role in producing heavy elements. This groundbreaking observation marked a new era in astronomy, allowing us to study the universe through both light and gravitational waves. It opened up new possibilities for research and deepened our knowledge of cosmic events. Neutron stars remain enigmatic objects, pushing the boundaries of our understanding of physics. Studying these celestial laboratories offers insights into the fundamental nature of matter and gravity. As we continue to observe neutron stars with increasingly sophisticated telescopes and detectors, we can expect to unravel more of their secrets. If you found this video interesting, please help us out by giving it a thumbs up. Thanks for watching, and don't forget, keep looking up.